So thank you all for coming. I'm Aleksandar Seovic, one of the architects on the engineering team, Oracle Coherence engineering team at Oracle. And this talk is not about coherence per se, but about some of the best practices when you're building scalable distributed applications. I mean, a lot of those practices I learned working on coherence and with coherence, but they're mostly driven by the fact that I'm irked to no end. I mean, I'm just frustrated as hell when people tell me that you should build stateless applications in order to scale. So this talk is really about showing you why stateless applications are not something that you can build, and why statelessness is not a prerequisite for scalability, and something else that you need to do. So before we get into the meat of the talk, unlike Neil Ford, who's kind of a nice guy and God bless his heart and everything, I do live in the south of US now, but I'm originally from Serbia, so I'm going to say it as it is. I'm going to call stupid things, and there is some explicit content in the presentation, so if you're offended, don't take it too seriously. I mean, let's try to keep it light. So here's the first stupid thing that I was able to find on the web. Right, so it says, it's one of the blogs, one of the things on the Rackspace blog. And it basically says, verbatim, bottom line, stateless apps are ideal. Server-side database writes are your enemy. If you must save state, save it on the client. Use cookies and AJAX where appropriate. If you follow this rule, you will multiply your scalability. And my first reaction to this is this. I mean, let's look at this thing line by line, really. I mean, stateless apps are ideal, yes, but if you don't have your state, what is your application doing? Server-side database writes are your enemy. Well, if you have to do it, you have to do it. I mean, enemy or not. If you must save state, save it on the client. Well, tell that to your bank. Let's see how it goes. Is what? Sure. If you follow this rule, you will multiply your scalability. Well, you're going to make your scalability infinite, but there is nothing to scale. I mean, there is no application to speak of, right? So that's one thing. The second one is actually worse, in my opinion, because you read it, and it kind of makes sense, right? It says services should be stateless. One benefit that you get from this is scalability. You can move expensive operations to a cluster of dedicated machines, and it does not matter which one responds to a particular request, since all of them are independent. And my reaction is, kind of makes sense, right? But can you really do it, right? I mean, can you make these services that are really truly independent? Because if your services are not managing your state, who is? Where is that state, right? And it turns out state is somewhere else, right? And your services are not truly stateless because they need to access that state. So another thing is actually something I almost completely agree with. I mean, there's some minor modifications I would make. So obviously I'm not calling this stupid thing. This is actually almost right. The internet can be thought of as a stateless system or machine. Most computers, human beings, and elephants are stateful. Exactly. One thing I would change here is, I wouldn't say the internet is stateless, I would say the internet protocol, HTTP, is stateless, right? And computers are machines. Applications are stateful. So here's the first fact. HTTP protocol is stateless. But here is the second. But your REST service that you build on top of it is not. To show you why not, here's the example of a truly stateless service. Anybody built service like this before? I mean, not very many people. Why? Because it's not very useful. You can do this on the client. I mean, why would you make a service and expose it remotely over web and pay network cost to do something that you can do in a browser? Right? I mean, that's your stateless service. This is not a stateless service. And this is what we typically do. you will have a service that takes some parameters. Based on those parameters, you will use some kind of repository or DAO, whatever you want to call it. Depends whether you like DDD or Spring better, right? I mean, different people call the same thing using different names. But the bottom line is you will use some kind of repository to get information from presumably database, but it could be anything else. You will modify that information within your service, and then you will write modified information back. Obviously, that's for mutating use case. For a use case where you simply want to read data, you will basically go to your data store, get the data, and then return it to the client, display it on the screen. Right? So that's really what we are talking about when we say, build stateless services. The problem with this is, do they really scale better? Right? Because that's the myth, really, that we are trying to debunk here. And in order to do it, I actually need a few volunteers for a really, really, really live demo. So I need 4 or 5 people, maybe. Come on. I'm going to start selecting people in the front row. I mean, that's what you get for being in the first row. Or actually, you guys are uncomfortable on the floor. Why? 4 of you, please. Come. Come on, I need a couple more. Okay. Oh, there you go. Rob, you're going to be a database. Kirk. Kirk, how are you doing? All right. So, Rob, Kirk, what's your name? Barosh? Yarek. Okay, you're a database. You stand behind those guys, right?
Okay. Oh, no one gets to see me. That's good.
Okay, so you guys are stateless. You don't know your name anymore. All right? So when I ask you what your name is, you have to ask Rob what your name is, and he's going to tell you your name, right? So you remember the names? Kirk? Bartosz, Yarek?
Yep.
Okay. Go ahead. What's my name?
What's my name? Kirk.
What's my name?
Bartosz. What's my name? Yarek.
Okay, now you guys start doing it faster.
Kirk. What's my name? What's my name? Yarek.
At the same time.
What's my name? Yarek. It's quite stressful. What's my name?
Thank you, guys. You're done. Yeah, as you see, it was quite stressful for Rob. And it's stressful for your database. When you have a lot of stateless services, they're just hitting your database. It is stressful. I mean, your databases are not designed to scale. So when you scale your stateless tier, and you have poor relational database on the back end, eventually it's going to start getting higher and higher latency, is going to become overloaded. And at that point, your scalability goes to hell. I mean, you don't really scale until your whole architecture scales. So the fact is that your stateless services really scale only as good as the state management layer they depend on. Which leads us to the big question. How do we really build scalable services and applications? And I have a couple of rules, and there are more, and you kind of have to think through and kind of try to eliminate bottlenecks in the application, etc. But there's some basic rules that you should heed. One, you should really separate state management and durability aspects. I'm not saying they have to be using separate technologies, but you should be thinking about them separately. So ideally, you should be managing state in memory using technology that allows you to scale, because once you have it in memory, and memory is cheap enough these days to do it, even for fairly large applications, the access to it is faster, right? We can do a lot more than we can do if we have to go to disk. And realistically, even databases manage most of the data that you're accessing in memory because they cache a lot of stuff internally, right? What I mean by when I say that you should use technology that allows you to scale, I mean, you need to think about, does your state management layer scale? Can you add more machines to make your state management tier scale better, right? And I have a couple examples here. This is probably the most recent one. How many of you are familiar? I mean, and it's kind of interesting because of microservices aspect that it covers. How many of you are familiar with lightband lagom? Not many, okay. Lagom, how many of you are familiar with Akka? A few more, okay. So lagom builds on Akka and effectively uses Akka for state management. But the idea is that if you have all these objects, all these pieces of data that your application needs to access, needs to manage, you should partition them across cluster of machines, across cluster of processes. So that allows, because partitioning is really what scalability is all about. If you can partition, you can scale. Right? The trick is partitioning and still being able to do some things atomically, still being able to query data, still being able to update data atomically, et cetera, et cetera. So what lagom does is it actually uses Akka cluster underneath to partition data. So this is really you have your Bob, Alice, Peter, et cetera. All your people are spread across the cluster of machines, backed up to another machine, et cetera, for fault tolerance. So that's your state management aspect. And then they actually write everything to a Cassandra cluster underneath, which is your durability aspect, right? So that's the way lagom does. And it's kind of the same approach that we've used in coherence for the last 15 years or so, right? We partition data across a cluster of machines. We have backups to ensure that if a node goes down, your data is still safe. And we really, until recently, focused only on that state management aspect. And then you were able to plug in whatever you want as your durability layer, right? You could use database, you could use file system, you could use whatever you want, really. More recently, we actually added persistence built in, so you don't need to plug anything else. You can have everything out of coherence. The same approach is used by Apache Ignite, which is another in-memory data grid product. This one open source, unlike coherence. And really the only reason, how many of you are familiar with Ignite, coherence? Few people. If you're looking to build scalable applications, I would strongly suggest you look in memory data grids in general. I think there is talk on Hazelcast later today. Should probably go there. Coherence is better, but sorry, had to do a little thing. But all of these technologies can use a similar approach. Partition data across the cluster, store it somewhere else, but allow you to access it in a partition, in a scalable, fault-tolerant way in memory. And then for durability, as I said, we added on this durability, and again, you could use Cassandra, you could use database, you could use anything you want really for durable aspect. And it doesn't have to be that fast because you're not accessing it as frequently, right? So all you want to do is make sure that your data is safe, right? So, and then there is another aspect. You can be durable on disk, but you also might need to be durable across data centers for DR scenarios. So you might need to support some kind of federation. And this you can do at a couple different levels. Some databases, data stores, they support replication at the data store level, so you could do that, or you could do, if your state management layer supports it, we've had for a long time something called push replication as an open source add-on to coherence. We actually moved it into a product and we are calling it federation now. So it's basically a feature that allows you to replicate data between grids across different data centers. All right, so rule number 2, and this is actually quite important. Design your domain model for the state management solution you're using. The way you design when you're using in-memory data grid, for example, the way you design your domain model is different than when you design it for a database. In general, if you want to partition data, you want to make sure that you're not working with small, database will tend to give you very, very finely grained chunks of data that you access from different tables and need to kind of pull them together to build your aggregate, right? When you're working with data grids, for example, you don't want to do that. You don't want to have cache per table in a way, right? Or data space per table. You want to have aggregate caches. You want to have your large objects. So if you have orders, you're not going to split it into order and line items, right? You're going to have order with line items in it and just put it in the cache because you don't have object relational mapping to deal with. You don't, a lot of issues are eliminated, but you need to think about what your unit of atomicity is, right? Because in most partition systems, it's really hard to do transactions. It's not impossible. It's possible, but it's not very efficient, right? It doesn't scale. to do transactions across multiple machines. It is much easier, much lighter, much simpler, much faster, and it scales much better to do transactions locally. So if you model your domain in a way that allows you to make all the updates atomically on a single entry, it makes your life much easier. And it doesn't always have to be single entry. I mean, we have notion of something that we call data affinity, which allows you to put related objects together. So, while order and order line items make sense to be kept as a single object, single entry in the cache, it doesn't make sense for something that keeps growing. For example, account and transactions. But you still might say, okay, I want this account and transactions to be co-located. I want them to be in the same partition, so I can basically post a new transaction and update account balance at the same time, right? And data affinity is a feature that allows you to do that. So you can control, to a certain degree, placement of related objects, right? As long as they have key that they can be related on. I do have a recommendation on a couple of books. I mean, the first one is Eric Evans' classic on domain-driven design. Really important if you're doing this kind of domain modeling. And really important if you're doing any kind of microservices work, which seems to be where all the fun is these days. Because what you're really looking for, what Eric is describing as bounded context, that's really what should map to your microservices. The second one actually builds on the first one, and I believe Vernon, one is actually talking in room number 1 right now. But it's also a good book, although for my taste it's a little bit more database focused than I'd like. I wish he covered a lot more other technologies, but basically he spent a lot of the material dealing with issues specific to implementing domain-driven design on databases, which is not an easy thing to do. So I mean, and it's justifiable because that's what most people still use, right? So I strongly recommend these 2 books. They will help you build better domain models for whatever technology you're using. Rule number 3 is do not move data unless you absolutely have to. And there is corollary to it, to send operations to the data instead. So let's talk about the first one here. I was actually, before this conference, I stopped at one of the major Polish banks in Wrocław for a meeting, their coherence customer, and they were having some questions and issues and whatnot. And it turns out they have this one cache, which is tiny, it's literally just a couple megabytes worth of data, that they're hitting over and over and over and over again. And they're doing this over the network. And their network is good, everything is optimized well, but they're still making like 100 to 200,000 requests per second. That is network latency, that is the cost, the real cost that somebody has to pay, right? So usually who pays it is the client trying to access the data, right? So there are a number of things you can do. I mean, because this is read-only use case, I mean, the easiest thing for them to do is to actually bring the data in process. And you can use features such as near caching, which will bring data into your local process on demand. You can use another feature that we have, which is continuous query cache, which allows you to bring everything proactively into the client process. Because this cache is small, you can literally bring the whole thing in process and access it just like if it was local map. And then if something changes on a backend, we will send the events and update all the local copies of it, right? So once they do that, I mean, they will remove 100,000+ requests per second that are going over the network. I mean, it should improve their performance significantly, right? The other thing is related to the right side of the equation. It is very inefficient in a distributed system to bring data to the client, modify. Like if you go and look at the first implementation of the stateless service I showed you, you go to your repository, fetch the data, modify it on the client effectively, even though it's probably your web server. It is a client to the data store, and then push it back. It is very inefficient, and it's also not very concurrent. With database, obviously, you have transactions, which means that you're starting transaction, doing your change, committing transaction at the end, et cetera, et cetera. With coherence, if you do it that way, you would have to use distributed locking. So you would have to lock the object, because basically you want to make sure that nobody else changes that object while you're changing it, right? So you have to lock, you have to get the object, change it, put it back, unlock, et cetera, et cetera. Each lock, each put, each write operation needs to be also backed up. So if anything fails, we still have everything that we need. So when it comes to it, doing distributed locking and get, change, put pattern will result in some 14 network hops for a single operation. What you can do instead is actually send processing to the data. So in database, you have stored procedures. You can say, OK, execute this stored procedure. In coherence, you have something that we call entry processor. So you can basically send entry processor to the data and execute it. So this is the example. We can say our repository has process method on the cart with a given user ID. I want to add this SKU and price, right, and quantity one. So this piece of code, this lambda that I have at the bottom, will actually be sent to the primary node that owns this particular cart, and it will do the operation locally without ever moving cart itself over the wire. So you can have a fairly large cart. You never have to move it over the wire unless you want to display it, right? You could do all the mutating operation without moving cart itself, right? And this is actually supported by something that we added, which is distributed lambda. So we can in the latest release of coherence, we actually try to adopt as many Java 8 features as we can, and lambdas were obviously the first and biggest candidates. So we actually added support that you can define lambda on the client, simply send it into a cluster and execute it. So you used to have to write custom classes for this, make sure that you're handling serialization, all of that. Now you can just send regular Java 8 lambda into the cluster. Another important thing, especially interesting if you're doing microservices, is that, but in other cases as well, is that you should do whatever you can asynchronously, which means that you should try to avoid blocking within your application. And the problem I have with typical microservices story is that REST seems to be the de facto standard on how microservices should talk to one another. And it really doesn't scale, it doesn't perform well, because if you use REST to talk between your services, it's okay when you have, when you're talking directly to a service. It's kind of okay when you have service talking to one another service. But when you have service talking to 5 other services, and each of those 5 talks to another 5 services, it simply doesn't work well. I mean, those latencies of going between one service to another service add up, and you end up having a system that really performs well and doesn't scale well because you're blocking all over the place. I mean, your CPU utilization is going to be low, but you're going to be sitting waiting for the I/O basically the whole time. There are a couple alternatives here. I mean, one thing, actually 2 things I've used are Socket.io, which is somewhat more mature protocol based on WebSockets, and HTTP1, and then you also have Google's gRPC, which is relatively new RPC protocol that's built on HTTP2. So both of these things allow you to do things. Well, Socket.io is only asynchronous, right? gRPC allows you to do things both synchronously and asynchronously, but you can use either of them to have your services talk to one another. Also, at a little bit lower level, when you start looking into code, I don't know if any of you were at my BOF yesterday, but we talked about in a lot of detail about completable futures and reactive and everything. One thing that we did in the latest coherence release, we actually added asynchronous API. And the primary driver for that is because we had clients who were saying, well, we can only do 1,000 puts a second, and they're doing it put in a loop, right? And the reality is, if we have to go over the network and then to another node over the network to do a backup and then come back, I mean, it's going to take 500 to 600 micros, right? So you can only do, you add proxy into the mix, and it's going to take a millisecond. So if you're doing 1,000 synchronous operations, 1,000 synchronous puts, you're only going to be able to do 1,000 of them a second from a single client thread, right? So you can do multi-threading on a client to split things up. You can do batching to improve things, etc. But in some cases, batching is not an option. Multi-threading tends to be difficult to do correctly, and still you need to figure out how to split things so you can do it across multiple threads. So we introduced async API, and the results were actually quite interesting from a throughput perspective, because where we could do on my laptop and on a test against 2 cache server nodes from a single client, single thread, I was able to do about 5,000 synchronous puts a second with a 1 kilobyte object. And with async API, I was able to do about 45,000, which is 9x, almost 10x improvement in throughput, right? So async APIs help. And with Java 8 completable future, building async API is actually quite trivial and nice. I mean, it's with future was kind of useless because future if you get a future, there is not much you can do with it. With completable future, you can compose things. You can actually build a whole async processing logic using completable future alone. Or you can upgrade to what Rob was talking about in his earlier presentation and go reactive, right? You can you have reactive extensions. You have Java, RxJava. You have Reactor from Pivotal. Akka streams, etc. So there are a number of reactive solutions out there that allow you to build very, very sophisticated applications that do everything asynchronously, right? So that's another thing that you should look at. Rule number 5. I mean, one of the big problems in distributed computing is, okay, how do I do long transactions, right? I need to do many changes. When I have an order is placed, then it needs to be paid. Once the payment is authorized, it needs to be submitted, packaged, shipped. All of that needs to be tracked, right? So how do you do those long-running transactions in a distributed system? Or how do you do them in any system, really? and the solution is really to model those processes as finite state machines and to basically use events that are happening on your objects as a way of transitioning those state machines from one state to another. So, the benefit of that is when you have state machine, you basically have state. When you have state, that state can be saved, it can be backed up. If that state machine fails from one machine to another, the processing can be restarted, right? Because whoever is watching for that failover can react to the failover of a state machine and basically see what state it is currently in and continue processing from there. So that's one way to do complex, long-running transactions, right? So rule number 6, don't use global locks, counters, so there are other stupid stuff that prevents you from scaling out. And I wish I could say that we as an industry are better than that, but there are many examples where people did something that prevents you from scaling. MongoDB had locks. It had global write lock initially. I mean, it's better now, but initially it had global write lock that literally prevented you from achieving any kind of scale. etcd and Zookeeper are fairly popular these days. Well, etcd more than Zookeeper. Zookeeper is kind of running out of steam since etcd and console came out. But they also both of them use global counters, which makes it really difficult. And they replicate everything. I mean, the problem with replication, as I said, if you want to scale, you need to figure out how to partition things, right? You need to partition data, you need to partition processing. That's how you scale. Problem with replication is the more you need to replicate, the bigger your cluster becomes, the more replicas you have, the more expensive every write is, right? Because every write needs to be replicated to more places. So that's really the problem with etcd and Zookeeper, and the fact that they have that one global index that they have to increment on every write operation. And when I saw that, both Mongo and this was my reaction. Oh, where is my tone? All right, you cannot be serious. That's famous McEnroe thing. It flopped, unfortunately. What could be what? Any kind of distributed key value store. If you think about what etcd does, it doesn't do much. etcd gives you put, get. It's a key value store, right? It's a key value store. It allows you to query keys within a certain structure. I implemented etcd on top of coherence in 2 days. It's really not that difficult, right? etcd API is fairly simple. It gives you events, but even events that they give you kind of suck because they give you in etcd2. They give you watch. They're better than Zookeeper. Zookeeper basically gives you events, But every time you get an event, you have to register again. It basically unregisters you, and you have to register again. etcd does the same thing, but they at least allow you to register again from a specific version, so you can get events from a history, right? The problem with etcd2 is they only keep last 1,000 events in history. So that's kind of, if I have something that is changing things heavily, I mean, yeah, maybe I'll get the next event, maybe I'll get an error, because it really depends on whether I'm asking for something that happened more than 1,000 changes ago or less than 1,000 changes ago, right? So those are not the greatest event. Any of in-memory data grid products will give you much better events, right? So, key value store with events is really all you need to implement etcd-like functionality.
Because it's particular, I guess, with ProOS and other things. It's
Yeah.
kind of native for ProOS.
Yeah, and Kubernetes uses it, and there are other pieces of the infrastructure that use it, right? So that's kind of why you want etcd API. But again, etcd API itself is 200 lines of JAX-RS that you can build on top of your KV store of choice, right? So it depends. And again, you might not need to do it. etcd might be perfectly fine for what you need to do. It just depends what kind of load and what kind of scale you need to use it for, right? I mean, if it does what it does, I mean, just use it, right? So I put this one last, but this really should be rule 0. I mean, we take things way too often at face value. We read it, we should build stateless service. I remember when 20 years ago, it's like, okay, Microsoft, what was it, Com+, DTC, you should build stateless services. Enterprise Java Beans came out, you should build stateless service. Like, yeah, that makes sense. But it doesn't really. I mean, if you start thinking about it, it doesn't really make sense, because the fact that your services are stateless is not going to help scale your state management layer, whatever the state management layer is, right? So whenever you hear statements like that, don't take them at face value. Think for yourself. Think if what people are saying actually makes sense. And I guess that applies to everything I've said today, because I'm assuming some of you feel like this by now. So with that, I will open it for Q&A, and we have actually quite a bit of time. I'm happy to spend on anything you want, or you can go and grab early lunch before the crowd gets bigger. Good timing.